Okay, so hello everyone, my name is Bartosz Szurgot, or Bash in short, and today I'd like to show you a little bit of measurements on C++ versus C, focusing on the embedded perspective. Without spoiling too much fun, I will just say this is going to be a sort of Mythbuster-like session. But before we start, let me give you a little bit of introduction. When it comes to me, I generally write software for food most of the week. I also try to dress like a bum to look more trustworthy in the IT industry. After hours, I am a professional geek. I work on Linux on a daily basis. I also work a little bit with the electronics, but I mostly focus on software. And speaking about the software, how many of you write software in C++ on a daily basis? Okay, a lot. How many of you write in C? Quite a few as well. Okay, and how many of you do embedded programming in general? Okay, almost half a room. Okay, great. So whenever I'm starting some new embedded project, C++ is my usual choice. Actually, many people associate my name with C++, but the funny thing is that it hasn't always been so. And today I'd like to start with sort of life-changing experience, because for many years I was actually a loyal C advocate, right? And today I'd like to show you what actually changed my mind and how it all started for me with the C++. And it all started with a little experiment. It was back about a decade ago. With a friend of mine, we had some sort of discussions. These were times of GCC 3.something and 32-bit architectures. And we had discussions C versus C, C++. And I finally made a bet with him that my C implementation of some simple problem will be just faster than his implementation in C++. And he said, like, no way, it will be just the same, right? You will just write it in a different way. So we clearly had a disagreement. So we did the only thing the two gentlemen could do under the circumstances. We wrote programs to check. So we defined a very, very simple task, just to iterate over some big array and just summing the elements that are inside the array and displaying the result. Trivial, simple, so let's give it a try. So I wrote my implementation in C. It looked more or less like this. So first I allocated 2 billion elements, some small 1-byte elements. Then I filled the array with some initial value. 3 is a very good number. And then I started to iterate over the array to sum the elements, obviously starting with the value of 42. And then once this is done, I freed the array and return some derived value from the result, so that just to make sure that compiler will not get rid of all my computations just because I'm not using the result. And that was my simple implementation. A friend of mine wrote something like this in C++. So again, he allocated 2 billion elements, now in C++ style, so new. And because this is a 2005, we do not have C++ 11, so he just used a boost scoped array. Then for filling, he actually used STL algorithm and iterator-based approach. And again, fill the array with the value of 3. And then he used accumulate to sum all the values, starting with value 42, and then return the result. And obviously, the array was automatically released when it was done. So we compiled the two elements and linked them and run them. How many of you would bet with me that C will win? Okay, a few hands up. How many of you would bet with my friends that we'll see identical results? Okay, a few more hands up. Okay, the result actually was that C++ was about 3% faster. And we are both astonished. Actually, in a way, we both lost our bets, right? Because neither of us was right. And, we are staring at the code like day 33 and we still suspect nothing. Like, where's the difference? And the truth is that, in a way, we wrote a slightly different code. A friend of mine wrote something a little bit more abstract, right? He said, I want to fill the array, not to iterate over array doing something inside the loop body. He said, I want to accumulate and then return the result, right? So thanks to this, thanks to using the STL, he actually gave some chance for optimizations to the compiler, because STL is used so widely, it's often optimized for a lot of corner cases. If you happen to have a type that for this particular CPU has an instruction that allows to do, for example, accumulating slightly better, then inside the STL it will be most likely used, right? So actually you get this performance for free because people who are experts in the field have already optimized it, right? And because of this, actually, they implement... I beg your pardon? Okay, I'll try to go a little bit slower. I hope we'll squeeze in time because I have like a lot of material. If I will cough 2 or 3 times, we'll not make it in time. Okay, but let's give it a try. So if you are interested, if actually sorry. not my pointer, I need to get used to it. If you actually replace the scoped array with, for instance, vector, you would get the same result, and it also the C++ implementation will also win, and the same pattern holds for both Clang and GCC. So the reality is that actually measurements tend to surprise, and in my case, this was actually a game-changing, because so far I just thought that C++ is all about these abstractions, and these are just expensive mechanisms that you need to pay for. And actually, this test showed me that it's not true. It's actually can be the other way around. All I need to do is to learn how to use it. And today, I'd like to show you some more examples of interesting elements that you can actually improve using C++. But before we start, let me define a sort of a proving ground where we'll test our code. We'll use a standard GCC with custom set of flags. Obviously, classical flags like debug and stripping of the binary. We'll also remove all the unused data and function sections. And last but not least, we'll use FLTO, link time optimization. And this actually is a game changer. If you are testing without LTO, this means you are not really testing the performance or the binary size that you could achieve if this flag is enabled. It allows to optimize between different compilation units, and it actually can yield very different results than when compared with classical optimization. So please remember about this flag. This is probably the most important one out of the ones I will show you. When it comes to standards, I selected C++ 11 and C99. This choice is not random. It's just the common denominator for all the tool chains that I have used. I mean, all versions of GCC for different platforms. And for microcontrollers, as usual, I just disable RTTI and exceptions. We could talk a little bit about this, but probably if we deep dive into it, it would take another hour. So for the purpose of this talk, I'll just skip this aspect. Now, whenever I will be talking about optimizing for speed is 03, was classic, and F inline limit equal 150. This increased the threshold for inlining, mostly when it comes to templates, because GCC has some nasty performance bug that if you do not enable the flag and enable C++ 11, certain constructions will just work much slower than they should do. So just to be on the safe side, we added this flag as well. And whenever optimizing for size, obviously OS. I think you are familiar with the flag when you're using GCC. Now, we have 4 different architectures that we'll be testing on. First is something you can think of as a modern PC. It's an AMD CPU, 64-bit, running at 4 gigahertz. It's using Linux, GCC 5.2, and as extra flag, Arc native to make sure that we emit code for this particular platform. The second one, smaller, will be ARM11. I've just selected the Raspberry Pi as the example because this is quite a common platform for developing, doing some home automation, stuff like that. This is a 32-bit CPU. Running at 700 megahertz, and also it is running on Linux and the same version of GCC and the same set of flags. So two platforms with the operating system. Now let's try to deep dive into more embedded world. So another CPU is ARM Cortex M0 as STM32F051. It's a 32-bit architecture running at 48 megahertz, but it has only 64 kilobytes for program memory, 8 kilobytes of RAM, so it's like a very small device, and doesn't have an operating system and GCC 4.9. So basically this is like a sort of mid-class microcontroller. It's not very small, but it's also not very powerful. And last and least is the AVR. This is the least powerful platform that we'll be testing. Atmega 8, the classic one. How many of you have used Atmega 8 in the previous projects? Oh, okay, quite a lot of hands up. Yeah, this is very popular among hobbyists. In fact, when you are starting with electronics, this is a good chance that you will start with the CPU. So 8-bit, 16 megahertz, 8 kilobytes of flash, 1 kilobyte of RAM. So like very, very small platform. And again, no operating system, a little bit older version of the GCC. Now, you can see that we have vastly different platforms. On one hand, we have PC with gigahertz. On the other hand, we have some small CPU, 8-bit, running at megahertz, right? And there is no screen, there is no keyboard, so how to test it? When I'll be doing measurements for runtime, I used a simple common approach, common framework that is being replaced for different platforms. It goes like this. As a first step, I just define all the elements that are required. So if I need, for instance, getting some runtime parameters, parsing them, this is done here before actually starting measuring. Then we start the measuring using internal mechanism, whatever is good for the particular platform. Then we put the actual code. So from now on, each time I will be telling this is the content of main, I mean this is the code that you should paste here. Okay? And once the code is done, then we can stop measuring and print the result. And once we do this, there's one more important step to get the output of our computations, whatever it is, some number, whatever, and print it somewhere as well, on the serial console, on the screen, anywhere, just to make sure that compiler will not get rid of it. Now, so we have framework. What about the overhead? When it comes to time overhead, it's fortunately very small. For instance, for AVR, it was like 5 CPU cycles or something like this, so it's basically negligible. When it comes to size, the rule of the thumb is it's around half a kilobyte, except for Cortex M0, where a little bit more initialization is needed, so it's slightly above 1 kilobyte. But the good news is that when we'll be comparing C, C++ and some maybe other implementations on the same platform, this will be a constant overhead, so we can ignore it in our comparisons as well. So let us first, before we go into the deep dive into a more complex example, let us define some sort of the baseline. Let's write the simplest C program, and let's try to write a simple analogous counterpart in C++. And let's try to test it. So first thing, size. AMD64, our attempt 1, and we can actually see that we have bigger binary for C++, right? So first test and first slab. That doesn't look good, right? So let's have a look closely what actually has happened. If you look at the linkage, you will notice that actually a C++ binary links against the very same libraries as C do, but it also includes a standard library for C++, even though we didn't actually use it, right? So it looks really bad here, right? We have extra library linked in, but we didn't ask for it. So what can we do? The first thing, we can just mark it linking as static, so we can make sure that into the binary we'll make only elements that are actually in use. So it means we'll include whole library for Linux, but on the other hand, we'll get rid of anything that is not being used. And now we can see that even though the numbers have grown, we have actually identical sizes, and in fact, they are MD5 identical, which means that we just generated binary identical files, so there is basically no difference in two simple programs, which is good, right? But the binaries are big. We can fortunately get a little bit smarter. We can also force GCC not to link the libraries that it is linking by default. This is a little bit of a fuss how to do it because it's, the commands are quite verbose, so I will not paste them. I will spare you 4 slides for this. But the basic idea is that it can be done, and when you do it, you have the binaries of identical sizes, and again, MD5 identical. So we have very same sizes without doing the static linking, which is good because this is what we are actually looking for. Now, having a modern PC done, let's deep dive into embedded platforms. So first, ARM11, our Raspberry Pi. Again, for static linking, sizes identical, MD5 identical. When we are doing without the standard libraries, we have the very same sizes as well. When doing Cortex M0, this is where funny things start, because we actually have a C++ binary that is 4 bytes smaller than C. And this is just by default for this platform. I do not know why, but indeed, in output assembly, there are just few instructions less, and the C++ binary are always 4 bytes smaller on this platform. So it's definitely sort of a myth busting, right? That you have actually have a smaller binary just because you change the compiler to C++, right? And on AVR, this is a simple platform, so most of the time you just get the same results for the same programs, and obviously MD5 identical. So on the embedded platforms, we're good as well. Now, what's the bottom line? Why is that? If you think about it, actually C is an almost exact subset of C++, right? There are some minor differences, we'll not get into details here, but basically C++ has all the legacy from the C language, so everything that you have in C is basically available in C++ as well. So as long as you are using this common subset, why would there be any difference, right? Modulo some maybe compiler glitches here and there, but basically, well, why there would be any difference, right? We are actually doing the same, right? So the C++ motto is you do not pay for what you not use. And as shown before, modulo this overlinking problem and one compiler glitch on one platform, there was basically no differences between generated code, the same code on C and C++ for the basic scenario, right? Now, let's try to do something more advanced. Let's start to do some flow control, more advanced flow control, right? Sounds like if, right? What can be interesting about the if statement, which is like so obvious to everyone and such a deterministic thing? Even Einstein once said that when you're doing something twice, the same thing twice and expect a different result, it's a madness, right? But this is because he never called IT support, and he has never heard, have you tried turning it off and on again, right? And the truth is that actually from time to time this really helps, right? So the question is, where's the catch? And the point is that actually even though from our point of view we are doing the same, we are running the same application over and over again, it actually different things happen in the hardware. Just think about this one simple scenario. You are rerunning the application, and it's put in this part of the memory. Application stops, you rerun it, and it's actually being run in a different part of the memory. So for instance, if you are accidentally relying on some uninitialized value, it may happen that the second time you will actually hit the value that just by accident is the one you were expecting, right? So the application will behave differently. So actually rerunning application is not exactly doing the same thing as previously. So, but anyway, when you are relying on such a thing, you make mistakes, and to make mistakes obviously a human thing, and effectively user will get errors like this, basically saying that universe sucks and there's nothing you can do about it. This is really not a good way to program stuff, and also it's unacceptable in embedded programs because there is no user that could restart your program, right? So let's try to deal with simple program that does a basic checks here and there, and let's start with C. Our simple application will go like this. We'll have some data. Let's assume this is some big structure filled with parameters. The first parameter is it's initialized with magic. Magic is some sort of a runtime value. It doesn't really matter what the value is, as long as compiler doesn't know it at compile time. Then, having the data, we initialize the data pointer, and again, it is being initialized based on the runtime parameter use pointer. And if it is set, then we use our pointer to data we have just initialized, and if it is not, then we set it to null. And then we use the pointer inside the loop, and we have three functions: function 1, function 2, and function 3. Each of them taking the pointer to the data as the first parameter, initial value, and returning the value back to the user. Why we have this magic 1, magic 2, and magic 3, the ifs? Again, this is a sort of a way of making sure that a compiler will not remove our code and our checks. When we enable link time optimization, as I said, this is a game changer, because from now on, compiler can reason, and linker, they can reason between different compilation units. And you actually would be surprised how many interesting conclusions compiler can reach if we're not be there. I was quite surprised. So just inserting these ifs made sure that compiler from now on can't really tell which function will be called as the first one. So basically, he needs to leave all the checks that are there inside. So the program is very simple. It's written in C, but as we said, the C is actually a subset of C++. So basically, we can just take this program and compile also using a C++ compiler. But before we do that, let's have a look at our three functions. This is the content. Please do not read the content of the functions. There's basically some garbage just using random parameters and random operations. The key point is that each function is different. So compiler cannot, again, assume that functions are the same, so we can make it one function in the output. And the most interesting thing is actually the error checking. Each function takes the data pointer, and before it can use it, it needs to validate it. And again, for the sake of discussion, not to get into details of error handling in different languages, let's just assume that we have very simplified error testing. If we find an error, we just abort the application. You can think of this abort as a sort of placeholder for doing real actions like logging, maybe throwing an exception in C++, whatever you can think of, right? Okay, so we have this simple test case. Let's measure it. First thing, the code results. So we have the very same code, identical, copied from C and compiled using both C and C++. We can see that C is actually 8 bytes smaller. It's not a big difference, but we can see that for this platform, compiler had some sort of glitch, and there was like slightly biased towards the C. But for instance, on ARM11 on our Raspberry Pi, it was the exact opposite. Actually, C++ version was much smaller. Like we have here over 200 bytes of difference, right? This is a lot. And this is, again, a common thing for this platform. In general, when you are taking C compiler, you by default get about 200 extra in binary size. Now, when we are checking Cortex M0, our mid-class embedded microcontroller, there is a small difference, 4 bytes. You probably remember from the previous slides that these 4 bytes are actually this difference that C++ versions always have a little bit smaller code, right? So this is the case again. And for AVR, classically, we have exactly identical binaries both times. And now, if we stopped here, we could basically draw the conclusion that maybe aside of one platform when the difference was significant, there's basically no difference if you take the same code and compile with two different compilers. But the question is, okay, if we take a C++ compiler, can we actually use it? And the answer is, yes, we can, right? We have this annoying thing of if pointer is not set, then do some error handling, repeating over and over again. So the question is, using C++, can we do more? And the answer is, yes, we can. We can actually write a simple template, let's call it not null, that will represent a pointer that is never null. How it works? First, this is a template of type P. The P is our pointer held internally. And we also, for user convenience, provide the arrow operator just to make sure that this is a drop-in replacement. So we replace pointer with the class, and the arrow operator still works, so it like feels natural for users. And also, inside the constructor, we use a reinstall initialization, resource acquisition initialization. So we take the pointer and we check. If the pointer is null, then we immediately call our abort actions, our error handling. But if the pointer is set, we just pass through, everything's fine. So once we have once we have created object of not null type, of some data, it means that this pointer is never ever null, right? It is already initialized and it can be used. So this view is obviously simplistic. For a real case scenario. It would probably need to add some more constructors and overload. But again, for our simplistic view, this is just enough. Inside the constructor, we make sure that a pointer is not null, and from that point on, we can just use this knowledge and update our main code. How the update look like? It's actually very simple. The main file actually needs to have changed just one single line. This is not null. Originally, this was a data star here. Now we put a template, not null of data, and that's it. Initialization stays the same. If we want to set the pointer, then set the pointer, otherwise null. And that's it. That's the only line that changes in the main. Now, what about the functions? Inside the functions, we actually do two changes. First of all is obviously change the type of the parameter, because we no longer take the pointer, we now take a template of the pointer. And inside, we also remove all the checks. Why? Why don't we need them? Yes, precisely. We already have a created object of not null. So we know that the pointer held inside is never null. So we do not need to check it. So we just remove the code. And the nice thing is, this is actually a sweet optimization. And also, it's nice for refactoring. Because once we change this, the very first line here, inside the main, and we just try to compile the project, we will get a bunch of errors pointing exactly. You need to change here, 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 and here, and it will work. Right? Compiler will just guide you through the refactoring. And once you are changing the type, you can also get rid of all the checks because they are no longer needed, right? So it's cool. And we are writing less code, right? And each time we write less code, we make one kitty happy. And this is a very, very good thing. Okay? So let's try to measure. I've copied the original results for C and C++ just for reference and added new column, C++ not null. This is our new improved version. So the original C-compatible code with actual changed type so that we now can ensure that pointers are not null at compile time modulo the constructor, right? So now we can see that actually our version is smaller than both of the previous. So we actually saved some code space, right? Around 20 bytes is for free here. Now, ARM11, the Raspberry Pi, similarly, we can see that we saved, it's not much here, about 30 bytes, but again, we have a win. And Cortex-M0, the same story. Here, it's small, it's 8 bytes extra, 8 bytes less, but again, we win. We have a free lunch here, and the same goes for AVR. So we can see throughout all the platforms, our slight change in the code actually improved things. And please think about it, what we have just done. We have created a template, spread it out throughout each and every compilation unit of our program, something that most people would say, well, this is going to be a disaster, right? Actually not. It decreased our code size. Using template throughout everywhere in each and every module decreased the code size. So think about it. Next time someone will tell you that using templates is just a footprint. It's not. It's the matter of how you use templates. You obviously can generate a lot of code and code bloat with templates, but if you use them wisely, you can actually improve things, including the binary size. But the binary size is not all, right? Let's try to have a look at speed. So when it comes to AMD 64, our modern PC, we have results in milliseconds, and we can see that pretty much the results are very similar. The differences are small, but the measuring errors, the standard deviation is actually quite big. So I wouldn't really draw any conclusions here. Similarly, it looks like for Raspberry Pi. Again, we have quite a big measurements errors for such a small program, so nothing conclusive. But the funny thing goes as we deep dive into embedded platforms. You can see that the numbers have grown rapidly. This is because the unit has changed. We now are talking about cycles, not microseconds. Why is that? Because we have no operating system, we have no preemption, and basically there's nothing that can get in the way of our measurements. So it is enough to start the timer in the background, counting cycles, and we can actually measure how long it takes for application to execute up to the cycle, few cycles precision. So it's a really great thing. And here we can clearly see that both C and C++ implementation took exactly the same amount of time, but our C++ not null version saved us over 6,000 cycles. So we again win in terms of performance. Same goes for AVR. Numbers here are even higher because this is an 8-bit architecture, so there is a lot of fuss about making some computations on a bigger types, but the general statement holds as well. So again, we have the same size for C and C++ and about 22,000 cycles saved in case of our not null approach. And again, think about it. Why? Because we spread the template throughout our usage, right? We weren't unable to measure any difference on the bigger platforms. Perhaps there is some small difference. Perhaps it's hidden by some hardware optimizations. Hard to say. We haven't measured it, right? But for microcontrollers, we can clearly see we have about 2% gain in speed, which is significant. For embedded platforms, every % gain is actually a nice bonus. So please remember this next time someone tells template is a footprint. No, it is not. Just use it wisely. Okay, I call this approach in general faster by encapsulation because we are using object-oriented term encapsulation to encapsulate certain properties. And faster because it is faster actually in multiple ways. First of all, it is faster in the development, right? So we are actually typing less code. Physically, we do not need to type if, right? It's also faster in execution time, as shown previously. And what is nice, it's also faster in testing. Think about it. How many times you have written automated tests that checked if you pass a null pointer to the function, it throws exception, returns some error number or whatever, right? You no longer need to do this because now you know this is checked, and compiler will always enforce you to do the check in the proper way. So you have actually one less test to write for each and every function. Moreover, from that point on, the testers that are doing system testing will also have less work to do because they will not need to report you some stupid errors like, hey, you forgot to check for null pointer here and application crashes and our testing is stopped, right? You can actually do it now automatically. So testers will be able to focus on real things like checking the business logic. So it's again, gain here. And as a completely free lunch, you have a smaller binary. And personally, I think this is totally awesome because you simply at the cost of writing one single template, you save your time for developing, performance, binary size, and basically you win on all fronts, right? This is not a common situation in the IT industry. Most of the time, you need to take trade-offs. There is basically no trade-off here. You just win, which is great. The approach obviously is a mixture of different techniques. I already mentioned some, the templates, the ROI. But if you actually look closely, you will notice that there is also a contract programming in a way. You can actually think about the constructor as giving a prerequisite for further computations. And from that point on, the compiler will make sure you do not break the contract, right? The approach itself is also very generic. If you think about it, I just presented probably the most common case, if the pointer is not null or not. But you could also check for a string that is not empty, or for instance, string that represents a valid name, or maybe the matrix that is square, or maybe the image for your image processing algorithm that is in an exact appropriate resolution that you are expecting, and so on and so forth. So basically anything that you can enclose in a sort of precondition, you can write it in constructor, and voila, it will just automatically work. So generally, this is a good practice to avoid the errors. And the approach itself has been field tested in multiple projects I worked in. And if you would like to give it a try yourself, it's available on my GitHub page as a part of basic utilities and tools library, and it's called Not Null. So we can just download it and give it a try. Okay, so we went through some basic flow control and what extra things we can do with C++. So now let's go to something that is a requirement for anyone who is doing a project that is larger than, 5 pages of code, which is generic programming. First, let us define a simple task. We'll be counting 4 medians on 4 different arrays. 2 of them will be of integers type, and 2 of them will be of double types. And just to make sure it all fits on the microcontrollers, the arrays will be just 10 elements in length. Now, the approach to computing the median will be to sort the array, and once the array is sorted, just select the center element out of it, and we're done. How do we sort? We'll be doing a bubble sorting and answering the question that pops up in your head. Yes, the bubble sort, and yes, I am aware there are better algorithms out there. But my point here is to show you some generic programming, not to get into computational complexities. So I prefer the algorithm that I'm sure everyone knows. So just for the purpose of this section, please assume that the bubbles are sweet. Okay? So the first implementation in C++, whenever we are talking about generic programming in C++, this usually means template. So let's go through the implementation. We have a template that takes a pointer to the array and the size of the array. Now, the most of the implementation is actually the bubble sorting. So we have this 2 for loops, and internally we check if 2 consecutive elements are in the wrong order, then we swap the order using the helper function, and we mark the flag that something has changed throughout the single run. If there were no changes within a single run, it means the array is sorted, so we can stop our computations here. And once we have a sorted array, it's just enough to select the center element, and we're done. Since we'll be testing this on embedded platform when there is no STL, no standard library, and so on, I also implemented a simple version of swap. It's not perfect, but for swapping integers and doubles, it's just enough, so it will do the trick. And also for convenience, I will use the trick to automatically deduce the size of the array. Once we have an array of a given size, we can internally call the implementation that will do the actual computations. Cool. Now, when we are talking about generic programming in C, we are basically left with macros. I'm personally not a big fan of macros because I find them as reading as Vogon poetry almost, because you have all these do whiles, this ending slashes, and this textual replacement that can really make your head hurt. But just for the discussion again, please bear with me, we'll go through the implementation. So first thing is to auto-deduce the size of the array, which is given as the parameter. We here assume that the array is on stack, but it will be fine for our test scenario. Then we have these two for loops, which basically means bubble sorting. Inside the bubble sorting, again, we check for consecutive elements which are in wrong order. If they are, we swap them. And we swap using a temporary parameter. And this temporary parameter needs to be provided by the user because we are just doing textual replacement, so we do not know what is the actual type. And we also mark the changed flag here. And if nothing has changed throughout a single run, it means the array is sorted. So we can return the result, but this is a macro, so we cannot directly return it. We need, again, to have an output parameter. So the output parameter that is given here as a part of the macro, as a part of the macro, we just select the center element and assign to it, and we're done. So let's try to go through the mains. Mains are really simple. First of all, we obviously declare the arrays. Again, we're using runtime-dependent values to make sure that compiler will not propagate constants throughout our programs. Then we need two temporary elements, one temporary integer for doing swapping and one double for doing swapping on doubles. Then we declare the output parameter and use the actual macro with the name of the array, the output parameter, and the temporary parameter. And the computations are done inside. And obviously, the pattern will repeat throughout the remaining three arrays. Now, let's have a look at C++ implementation. The very beginning is exactly the same. So we are just copy and pasting the array to have the same values. Again, runtime parameter dependent. And then we are just calling array median. It's like beautiful because it's just one line, right? We just pass the name of the array, the size is auto-deduced, and since this is a function, it returns a value, so we can mark our output parameter as const auto. So the type will be auto-deduced and it will be automatically marked as const because we do not want to change it. So it's like very nice and readable. And we'll do the very same thing for the remaining three arrays. Now, if you look at it from the distance, you will notice that C++ implementation is actually about half as short as the original C one, which is good, right? We have less code. But in order to achieve this, we had to use three distinct templates, right? So what's the first question? How about the size, right? So let's measure. And we can see that AMD64 without the standard library, we can clearly see that C++ implementation is over 600 bytes smaller than the C, so it's a big win. Same goes for ARM11, again, around 600 bytes less. Cortex M0, 100 bytes less. And for AVR, again, around 200 bytes gained. So if you look at it, you will notice that because we use the C macros, we actually made the bigger binaries, right? So the actually templates helped us to generate smaller binaries throughout all the platforms. On non-embedded platforms, the difference was significant, but again, on the embedded platforms, even small difference can really matter. So we actually won on all fronts here. So how many of you are surprised to see this result? Hands up. Okay. Okay, quite a few. Okay, we'll be talking about it in a second. But before we go there, let us measure the speed. And again, yes? Yes? And no, this is built-in templates. The question was about the templates. Where are they taken from? These are templates supported by the compiler natively. No magic here. Just regular templates from the GCC. Okay? Okay. Let's measure for speed, and AMD64. We again can see that results are the numbers are very small because we had very little data here to test. So nothing conclusive here. Same goes for the Raspberry Pi. Small results, big errors, so nothing consecutive. But again, if we deep dive into the embedded platforms where we can measure CPU cycles reliably, then we'll notice that we have about 1,500 cycles less for the C++ implementation. So actually, it turned out to be even faster. And the same goes for AVR, around 15,000 cycles saved. So the same pattern holds. Actually, C binaries generated slower code, right? And for the embedded platforms, the difference of 13% is actually something significant. So, feeling surprised again? Okay. So the observation was that C++ templates actually outperformed macros and actually generated smaller binary. So the question is, why templates won? If you think about it, whenever you are using template, you are actually creating, in a way, you're creating a function. You're generating a symbol, right? But it's a symbol that compiler and linker can actually inline or just leave it as a function call, depending on what is believed by the compiler to be most optimal for a given set of data, including the parameters, right? So in a way, by generating such a function, you give a compiler hint. Hey, this is a piece of code that repeats in different places, so you might want to make it a common thing, right? So we can clearly see now why there was no problem with code size when we were using the templates, right? Because we could use inlining if it improved things, but we could also leave it as a function if a compiler decided that no, the size actually would grow there. So the question is, why macros lost? If you think about what we did with macros, macros are actually a preprocessor-supported way of copy and pasting code around, right? If you think about it, if you just remove the macro and copy and pasted code everywhere when the macro was used, you would get exactly the same result because that's how macros work, right? Before the processor even, before the compiler kicks in. So you basically did not generate any symbols, so there were no hints for the compiler, and basically compilers usually cannot find the piece of code that this particular part of this function is actually the same as this part of this other function, right? So you cannot really expect compilers to get such knowledge because it would be just too expensive in computations. So basically, when you are using macros for generating code, you are generating a code bloat. So this is why we have the problem. And the overall observation is that actually C lacks a good support for generic programming. I mean, there are some mechanisms. Okay, you can use macros, but as shown previously, this can be actually quite problematic. Because first of all, because of the problems shown, and second of all, because macros do not respect language rules. This is about the textual replacements, so we can get really weird effects if you are abusing macros. And so, what's the alternative? The common approach in C is also to use the void star API. How many of you like void star APIs? Okay, I don't think I see a single hand up. Okay, this is precisely my feeling. You have a function that takes 7 void pointers, and now try to find in documentation what do they mean, right? If there are pointers, maybe pointers to structure, pointers to values, pointers to functions. Wow, crazy, right? And by the end of the day, you will have a code that passes all the pointers around, and even assuming that you do it 100% correctly, you internally will need to have a function called to your functors operating on parameters. So effectively, you might end up having a function call for such a simple thing as comparing two integers to do the sorting, right? And this is disaster when it comes to performance, and it actually doesn't improve when it comes to code size as well. So it's really bad thing. LTO, link time optimization, might help here, but it's first of all, it's not guaranteed, and second of all, you're actually relying on having anything useful out of your compiler on a very particular optimization, which can be actually quite a risky thing. So not really a good way to go. So basically, C lacks good mechanisms for the abstraction. Now, we made it through the flow control. We showed some generic programming. Now, let's have a look at some conclusions. First of all, my personal observation when I was preparing the data for this presentation was that actually compilers do amazing job optimizing. I actually literally had headaches trying to figure out what the hell just happened that my binary is definitely too small for the task, right? Why is it so that I'm adding a function and my binary is not growing, right? The text size is constant and the same. And actually, I constantly was finding the edge cases where compiler find it out that, hey, you're using a constant value. I can propagate it here, and here, and remove these branches, right? Or a compiler could actually figure out that some parts of code are not really needed. I am doing a lot of important computations, but I'm not using it, so I can just get rid of it, right? So there are a lot of such things. There are also thresholds for inlining, which function to inline, which one not. And this is just the regular compiling. If you are enabling LTO, as I did, you actually go like one layer up, because all of these optimizations can also take place in linking time, completely rearranging your program. And this is just a yes? Yes? No, I just use different mechanism. I just ask compiler to display the result, but outside of the measuring loop. This was the last function call when I showed the template for measuring. The very last call I did was just sync the result, right? It usually on PC it was just printing on the screen. On embedded platform it was just sending it via serial port. Doesn't matter as long as compiler knows that it is used. Using a volatile, yes, this could be another option. This would probably break this optimization as well. Okay, so once you're through with all this optimizing, compiling, you will actually notice that you have one more thing to do, right? You need to run it on hardware. And that's when funny things start, because you have multiple CPUs, pipelines, branch predictions, caches, memory coherency, superscalar architectures, and probably half a dozen other optimizations I just forgot to mention here, right? So it's like completely crazy. Because it's really hard to reason about it. And whenever I'm trying to reason about all the software and hardware optimizations together, this is the first image that comes to my mind, right? I don't know if you have played the Incredible Machines, right? So we have this very complex system that even if you like touch a little small innocently looking thing, this can actually just turn out the results upside down. So whenever you are testing, you need to make sure that you are actually doing tests on actual algorithm that you want to use, and the algorithm actually use the data that we would use on a production system, because otherwise you may actually be measuring something very different from what you expected. So we can get very, very surprised, right? And when it comes to this, actually testing on embedded platforms is a really nice thing, because you have this small CPU that when you're done with doing software optimizations, on hardware level, not much actually can surprise you. This is, for instance, a picture of the test bed I was using for testing results of this presentation. You can see the STM development board, the AVR at Mega development board, and they're just very predictable, right? If you are done, you know what has happened during compilation and linking. On the hardware level, there's basically not a thing that can surprise you, because they're just executing commands one after another. That's relatively simple compared to what the modern CPUs, like big architectures, does, and you then can have totally crazy results, right? So in a way, if you are doing embedded programming, once you have the test framework established, it's actually easier for you to reason about what is happening, because there are just simpler processors. Now, going back to our original theme, C++ or C. In my personal opinion, actually nowadays C should be avoided. It's not true that it's just generating the smaller binaries. It's also not true that the binaries are faster just by mere using C. The truth is, however, that C actually is lacking abstraction mechanisms. And when we are running out of mechanism, we need to work around this, and this is where these code monsters actually start to appear, like multiple macros nested in one another. And this is really a nightmare when it comes to creating, debugging, analyzing, and trying to figure out why it's not compiling on a new platform. You might, however, still consider C an option, first if there is no other option. And however funny it may sound, there are still some niche platforms for which you basically can have only a C compiler and there is nothing else, because it's such a niche that not many people are using it. So you can still have such a CPUs, and for them, the C is basically the only way to go. You can also have a C-only team. C++ is powerful, but it's also quite complex. You need to get used to it. And if you do not have at least one very experienced C++ programmer, you actually might find yourself in the trouble. And also, there is a thing of common ABI. When you have C++, the ABI is not really that stable. On C, it's actually well known and commonly accepted. So if you need to provide the binary interface for different applications, actually this can be a reasonable way to go. It's not a must. You might actually find out that even though we are distributing binaries to the users, they are compiled using the same toolchain that you use. It's a quite common situation in corporate environments when there are different teams, and one team is providing some functionality to the other, and they provide both the binary and the headers. But there is a common toolchain for whole project, so basically there is no risk of breaking this ABI, so you can safely just use the ABI for C++. But if for some reason you truly need the stable ABI, then C would be the way to go. And in fact, even if your implementation is C++, you might want to cover it with C implementation just to make sure that the ABI remains stable. So my advice would be that for the embedded development, C++ could be used as the default tool, because it can do everything that C can do, and as a free bonus, you get the extra abstractions. You can use it to improve things, but if you think it's not worth it, it doesn't really fit in your domain, you can just ignore it. But you have it, you have the option if you need it. And yeah, speaking about C++, which is by itself, it's very powerful, there are also incredible sets of libraries, right? So how many of you would say that you can implement HTTP client in C++ in, say, 10,000 lines of code? Hands up. Okay, very few. How many of you would dare to say that will be 1,000 lines of code? Oh, very few. Someone would dare to say 100? 2, 3, 4. Okay. Yeah, actually you are very close because the correct answer is 10. This is actually the fully working example of HTTP client. So once you find a reasonable, actually like 10 lines, but if you think about it, if you remove all the boilerplate, you can actually do it in 4 lines, the content of the main, right? So once you find a reasonable library with the simple API, you can just use it out of the box and it will just do the trick for you, right? And aside from this, the standard libraries also grows rapidly, right? But it still obeys the rule, you do not pay for what you are not using, which is the whole motto for the C++. So basically, you can use heavyweight mechanism memory allocations, but only if you choose to. If you do not wish to pay for the price, you can always select the other mechanism and you're good to go, which makes C++ very, very embedded friendly environment. Now, to show you that it's not like just the theory, I've made a project, a pet project a few years back. It's called the Doorlight project. In a place where I live, it's very dark. Once you approach my doors, it's literally dark in the evening. So I decided to glue the strip of LEDs above my doors, and there is a motion sensor with the board to control it. And the motion sensor obviously works as a proximity sensor. It has adaptive noise filtering because there are different lighting conditions, and there are also sleep modes. There is a watchdog implemented. There is power monitoring because actually the device comes in 2 different variants. There is DC powered and the battery powered one, so we can select. And all of this is written in modern C++ 11. It's about 900 lines of code, and it's less than 800 bytes of the binary size. And all of this is actually running on AVR80Tiny13. This is a small CPU running at having 1 kilobyte of program memory. Think about 1 kilobyte program memory and 64 bytes of RAM running at 1 megahertz. And the system is already running for, I don't know, over 2 or maybe 3 years and counting. So it's like real thing. So I hope I managed to convince you that actually C++ is a really good tool for the embedded. If you would like to read more, then you can go into the other materials. The presentation will be supplied after the show, so you can read through them. There are some books and publications that are worth reading. If you think, for instance, that using exceptions is expensive, then I highly recommend Technical Report on C++ Performance. There is a separate chapter there dedicated. Just to make a long story short, it's not that simple. Okay, so I presented quite a lot of things today, so if you have any questions, do we have time still?
10 minutes.
10 minutes, great. So if we have some questions, then there are runners with the mic, so please ask them.
Okay, before I open the floor to the questions, just a quick fact about Finland, the country that the company comes from. Did you know that in Finnish language there are no genders, like male, female, neuter? Thank you. I couldn't help noticing that all the speakers today and all the people who were asking questions were male. So why don't I ask ladies first to come up with their questions? Girls? Sorry about that. Okay then, anyone then?
Back to regular.
Over there, please.
Thank you. Nice presentation, especially with this optimization with
I'm sorry, can you speak to the mic?
Hello, can you hear me now better? All right. Could you get back to one of the first slides with the example with not null semantics?
You mean the implementation?
Yeah. My problem with this example is that it is a bit conveniently academical because you are using RAI-style initialization, which in practical implementations requires like throwing graceful handling, like perhaps throwing exceptions and catching exceptions. Catching exceptions requires enabling exceptions. So this requires enable this option in the compiler, which grows the code size.
Okay.
Could you comment on this?
Yes, thank you. This is an excellent question. So the point is that we have a board here, right? What would we do in the real code, right? I said this is a placeholder, and obviously, as usual, the right answer is it depends. But in fact, if we are not doing the deeply embedded programming for microcontrollers that have like, I don't know, 10 or 20 kilobytes of program memory, actually throwing an exception is quite a good thing. I said I will not talk about exceptions and RTTIs, but there was an explicit question, so I will just say a few words. It works like this, that when you have an exceptions enabled, your binary can grow usually between 5 to 10%, that's true. But on the other hand, if you are using exceptions and you have the scenario when you are not throwing the exception, it is actually faster than using return codes, right? So if the exception is thrown, it's significantly slower, that's true. But if you are not throwing the exception, it's actually faster. So that's like one of the interesting facts. I highly recommend reading this C++ report on performance. There are details why it's so and how does it work internally. But my point here is that actually throwing an exception in the embedded environment doesn't necessarily need to be such a bad thing. I agree that for small microcontrollers, yes, this might be a problem. But on the other hand, if you are writing code for something that has like 2 or 3 kilobytes of program memory, there is a good chance that you can just assume that pointers are not null because you are not doing any dynamic allocations and stuff like that, right? So most of the time you can forget about it and, for instance, insert here simple assert that will be removed in the release version. So in the debug version, you make sure that your assumptions are right, and the release version, it all goes away, right? And for anything bigger, I would say that you can freely use exceptions as long as this is not a real-time, hard real-time code. Then it's a bad idea, but in general, I don't see a problem here. But thanks for your question. This was a very good one. Yes? Please monitor time. My watch just went off, so.
Hi, hello. You said, while comparing macros to templates, you said something like template was optimized to something like inline, where you put it here, here, and here, so you can use in fact, a symbol, which shortens the binary file, in fact, a little bit. While in macro implementation with C compiler, you put the code here, here, and here, and the compiler doesn't optimize this procedure.
Yes.
So the binary grows.
Yes.
Having the first time collision C and C++, someone said to me that inline is exactly like macro because macro put codes. Could you say something? Yeah, why this symbol that was an optimization from template is in fact
okay. So like two things here. First, when you are declaring something as a function as a template, it is like implicitly marked as inline, and you can also explicitly mark any function, not necessarily template, as inline. But the point is that marking anything as inline is just a suggestion to the compiler. I would prefer this one to be like, in a way, copy and pasted into the place of execution. But actually, the compiler makes the final. No. Compiler, no, when it comes to macros, actually macros go before we do compilation. So first, the macros are expanded, so we have already pasted code inside, and then the compiler kicks in and try to analyze the code. So once the compiler, what compiler actually sees is exactly the same as you would manually copy and paste the code. So it's Yes, yes, this is done, but sorry, yes, thank you. So the remark was that the inline is actually also a copy and pasting things, but inline is just a way to signal compiler that probably it's a good idea. But as I said, compiler can choose. And for instance, if you are compiling with optimizations for speed and for size, you can have very different outputs. For instance, if you have a function template that operates on some big data, like big structures, it actually might be worth to keeping it as a symbol because there is a lot of stuff happening inside to make all the computations. But on the other hand, if you pass parameters that is an integer, there is no problem. The code is small, so why not just put it inside of place of executions? And actually, in the example I have shown in generic programming, somewhere here, yeah. if you look at it, this is a template, this is a template, and this is a template, right? But actually, if you look at this, there are like three very different things. Here, we are basically doing three operations. We know that there's our integers and doubles, so there's all like small operations. So it would be a good idea to put this in place of execution. So here, right? Same goes for here. This basically generates no code. It's like semantic sugar to automatically get the size of the array, right? It doesn't generate any code at all. So in fact, there is no point to making symbol out of this anyway, right? And when it comes to this, actually here a lot of things happens. We have multiple loops, some variables, and so on. So actually it might be a good idea to leave it as a function call. For instance, when we are optimizing for size, right?
Two more questions waiting, so please keep them brief. Gentlemen over there.
Raz, dwa, trzy. You mentioned that we can use so many C++ libraries. But what about the dynamic allocation that a lot of them needs under the mask?
Mm-hmm.
Do you have some simple answer or reliable implementation, for example, for STM?
Okay, so when it comes to memory allocation, when you are using memory allocation, it usually means you are having a bigger CPU, perhaps even with the operating system, right? So when you're asking for a good answer, there is no such thing, right? The longer I am in industry, the longer I find, the more true I find that actually each problem has a slightly different solution depending on the architecture or on the actual use case. So I wouldn't really want to give you any general advices here, right? You just need to select a proper tool for the proper job, right? If you would like to have something that will, for some reason, allocate the memory on the microcontroller when there is no operating system, you could, for instance, write your own allocator to do this. This is possible, right? But when it's like a small microcontroller, you need to be aware that you do not have a memory control unit, and you actually need to know what you're doing and make sure that, for instance, there will be no memory fragmentation. So there's like, it's a really huge topic, right? So the decision definitely must be made based on the project-to-project basis, right? So if you have very small project, this is probably, on the small microcontroller, this is probably a very good idea to do dynamic allocation. On the other hand, if you have full-blown PC, this is perfectly normal. Everyone do it on a daily basis, and it's perfectly fine, right? So there are a lot of trades-off here, but project-to-project basis in general.
Okay. So you did mention.
Sorry, can you stand up because I can see you? Okay.
Here. Yeah. You did said that there is no trade-off when using C++ and templates, but there is one.
Template C++4?
No, for this kind of stuff, yeah. What I mean is that there is one trade-off, and this compilation time probably it's a little longer.
Yes, that's true. So in general, templates do increase compilation time, but on the other hand, if you think about it, well, in a way, you always pay a trade-off, right? In case of templates, they can help you automate things, right? If you write template, you want to have some sort of genericity for some reason, then yes, you can have increased compile time. And my personal opinion is just find the right balance, right? If you look at the libraries that are there are very different libraries. On one hand, you might have such a simple template as swap, which is just nice, and it will not compile for ages. But if you try to write a parser using Boost Spirit, it's the other way, right? You can have like 10 lines of code that will compile for half a minute. So again, just like choose the right balance. If you really need you need to really do a lot of generic programming, then okay, you might want to consider just limit yourselves a little bit, and from time to time just write something manually, because generating it would take ages, right? So again, project to project basis.
Thank you.
Thank you very much. If you've got any more questions, please leave them for the break or indeed for the after party.
Okay.
I've got two quick announcements just before we go, if that's okay.
Yeah, I just wanted to say thank you for nice discussions, and since we're in a very since we're in a very good for discussions, maybe next year I'll try to do Vim versus Emacs, right? Okay, thanks and enjoy the rest of the conference.